Here we go. In continuation with our previous question answers, in which we have seen up to 10 questions, we'll see another set of 10 there. And here is the question is, what is the complete IUPAC name of the following substance? So he's asking the name. The reason is, it is having two asymmetric carbon atoms there. You can see here, this one and this one. Okay. So that means you have to take up separately on this. So I'll take this one and put it like this, CH and then OH, and then this particular bond. Okay. I'm just taking up this bond there. Right. So it is having one C and is connected to another ring like this. So it goes on like this. And here is another bond that is there. So this one is shaded. Okay. And this one is fully shaded, and that one is partially shaded. That is means it is coming up, and this one is going down. Okay, so you have to put separately and find out which one is R and which one is S. Okay, so let us give the numbering like this. So I give numbering accordingly like this. This is 1, and this is 2, and this is 3, this is 4, and this is 5. So you have a 5-ring system there. So first you give the number, and either if you start from 1, 2, 3, 4, it goes to 4. So you have to number here. If number puttingna in the 1, 2, 3, 4 வந்துரும். அங்கே 1, 4 வரல, இங்கே எங்கேயும் 1, 3 தான் இருக்கு. 1, 3, 1, 3, 1, 3, 1, 3 தான் இருக்கு. There is no 1, 4. So this is the right numbering there. So if you have numbering, so you have to just find out whether it is 1 is R and 1 is yes, or 3 is R or 3 is yes. Okay, right. The next thing is you can check how this group goes. Here you have only one CS2 here, and then there comes a hetero group in which you have one O there. But here you have got one CS2 and then another CS2. Here you have got one CS2 and then you have got a big molecule there, OH and CS3. So you get a heterocyclic group there, and then it is connected like this. So priority will be, this will be the last priority because of hydrogen. The next will, this is the last. Okay, the first priority will be given to oxygen. If you check this, oxygen is having an atomic number of 8 and its molecular weight is, its atomic weight is 16. Therefore, you have to give this the first priority. And between these two, if you see, here you have CC, here you have CC. Then you go for the next. Here after CC comes C. Here after CC comes O. So therefore, this will be the second priority and this will be the third priority. Okay. Now, if you look at this, 1, 2, and 3, you can just directly put it like this. So 1, 2, 3, it goes like this. So it is clockwise. So when this clockwise, it will be R. So 1 R and then 3 will be in the opposite direction. So 3, and if you take up this, you can just work out. If you work out this, you will get 3 going in the opposite direction. So 1 R and 3 S will be there. So the D will be the right answer. So let us just check into what is there in this explanation. The IUPAC name will be 1 R and 3 S because it is 1 methyl cyclopentane, 1 3 diol where 1 position source R and 3 position source yes. That is the answer there. Okay, this is the answer. So you can work out. So again, I can just draw a corollary, a similar diagram like we have done for this. See, here you will have OH and here you will have CH3 and here you will have CH2 going up. Here you will have one CH2 and then CHOH will be there. So the last priority will be, which one will be the last priority there? All of them are CH3. Here you have 2 CH2, so this will be the last priority, fourth group. First priority will be O, second will be this one, okay, and third will be this one. So you can see that it goes in 1, 2, and 3 in the backward direction. So this is anti-clockwise. So when it is anti-clockwise, it will be yes. So this is yes, that is there. Okay, for this particular atom. Right, so we move on to the, so it is not clear there. So we move on to question number 2, that is how many stereoisomers are there for the following structure. I think you can just take up that particular formula. In the case of 2,3-dihydroxybutanedic acid known as tartaric acid, this is a tartaric acid, 2 chiral centers are there and both are equivalent. As a result, 2 the 4 esters of this compound are identical due to the plane of symmetry, so there will be only 3 isomers. So what it is telling is, you can see the answer there. I just below, I'm just showing the answer there. Here it is. So how many asymmetric carbon atoms are there? There are 2 asymmetric carbon atoms. So 2, n equal to 2, and number of isomers equal to 2 power n, and therefore you got 2 power 2, which is equal to 4. You should have 4 isomers, but what is happening is you are having a plane of symmetry. Where is this plane of symmetry? This is it. In particular isomer, if you rotate this, you will have one plane of symmetry. So if you have symmetry, then you have to remove. That is what, as a result, now the 2 chiral centers are the same 4 substituents. Okay, this is a chiral center and this is a chiral center. Chiral center 1, chiral center 2, and then both are having the same H, H, OH, 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 OH. So there will be one isomer in which all the isomers will be the same. So this, we call it as the equivalent. When you have equivalent, you should put 2 isomers equal to 1. Therefore, you should remove -1 and you will get the 3. So the answer is only C. So you get only 3 isomers. So there are only 3 isomers to the tartaric acid because one isomer is mirror image of the other one. Okay. How many stereoisomers are there for the 3-bromo-2-butanol? And it is actually, again, you have to write the structure there. Each chirality center can have either S or R configuration. For a compound vinyl chirality, there is a possibility of a maximum of 2 instead of this. You know very well about that. So let us write this structure and find out what is in store for us. So it is CH3, CH, and then OH there, and then again another CH, and then Br there, and then CH3 there. So there are 2 asymmetric centers. One is this one, the other one is this one. We can just take up this one. So when you have 2 asymmetric centers are there. So 2 power n equal to 4. You should have 4 isomers. And you can see that there is no mirror plane. Therefore, you can just take up the 4 as the answer. So D will be the answer there. D will be the answer. So if they ask you what is 1 and 2, you can give them the numbering there, right? So you can give this the number. You can give this as number 2, and then have this as a lower priority. First priority is this one, CH3. Second priority will be this entire group 2, and third will be this one. Sorry, this will be first priority, this will be second priority, and this will be third priority. So the group will go like this. So it will be anti-clockwise. Therefore, it will be yes configuration for the first carbon atom. If they ask a question like this, but they are not asking. So let us move on to the next question there. Fourth one. How many stereoisomers of 2,3-butanediol exist? So again, you can write butanediol, CH3, CH, OH, okay, and another CH, and then OH, and then CH3. So now you can see that there is a mirror image that is existing in between. So you can see that this is a plane of symmetry is there. So this is called as the plane of symmetry is there. Okay, but you have got 2 chiral centers. So one is this chiral center and another one is this chiral center. So you should have 2 power n equal to 4. But because there is plane of symmetry, 2 isomers will be identical. When 2 isomers is identical, you can take these 2 isomers as one isomer, and you have to subtract 4 minus 1, so you get 3. So 3 is the right answer there. What is the answer there? 3 is the right answer. A is the right answer. So here is an explanation is given there. A very good explanation. and each chiral center can have either yes or on configuration. So you can just find out which is yes or which is R. You give this as last priority, you give this as last priority, and then first priority will be OH because O is 8. This will be first priority. Second priority will be this bulky group. This will be taken as one bulky group, so you put as 2 and this as 3. So you can see there's 1, 2 and 3, it goes like this. So it is anti-clockwise, therefore it will be yes if you are to calculate the R and S configuration, but that is not being asked. So it gives 2R and 2S, or 2R 3S and 2S 3R compounds. This is the chiral meso compound. So you can get a question whether DL mixture is there, meso compound is there. This one is a meso compound where you have a plane of symmetry, where you have plane of symmetry, you will get a meso compound. And or you if you mix the two, one is D and the other one L, you call it as a DL mixture. So this question will be asked in your future. So you keep in mind that those things. For a compound with n chiral distance, there is positive maximum of 2 in isomers. The same thing is repeated there. Now let us move on to question number 5. What is the complete IUPAC name of the following isomer? Again, this has the same thing as IUPAC name means you have to give the S and R notation for that. So just to find out how many chiral centers are there. How many chiral centers are there? One ethyl, 3 dimethyl cyclopentane, and where is one position? So you have only one chiral center, right? There are no more chiral centers. Why? Because you can see that here this is group 1, this is group 2, this is group 3, and this is group 4. Here you have two similar atoms. These two are similar. Okay. So you have got only one chiral center. And you will have only 2 power n equal to 2 isomers. Okay. Out of this isomer, he is asking which one is this yes, or which one is which is yes, and either yes is there or R is there. So for that you have to draw the structure. Look at the answer is the C. How do you get into that? You can write even Fisher projection formula like this. So the top H will go here. Opposite of that will be C25. So here you have one bulky group with one CS2. Here you have one branching CS3, CS3 and one CS2, CS2 there. Okay, you just take up this last priority. First priority will be, which one will be the first priority? This one will be first priority, this one will be second priority, and this one will be third priority. So you go 1, 2 and 3. So it is anti-clockwise, and therefore it will be yes. So that is the 1 yes C is the right answer. 1 yes, 1 ethyl, 3 dimethyl cyclopentane. 3 1 2 3 4 5. So 1 yes, that is 1 is having yes configuration. That is what you are just putting here, yes configuration. One ethyl group is there. 1 yes, okay. 1 ethyl, 3 dimethyl. 3 dimethyl means this is one methyl, this is another methyl. This is for the third carbon. 3 dimethyl. The entire group is cyclopentane, 5-member ring. Okay. So that is why you just put it like that. Okay. So now moving on to question number 6. Which of the following structures represent the same stereoisomers? So I think you have to do a workaround for that, and the answer probably is, can you see this? A, B and C. Here you have 2 and 3. Structure 2 and 3 will be there. Answer is B. Okay. So let us see how the explanation is given there. So very beautiful explanation is given there. B is only 2 and 3. How? You see this carbon atom? Cl, CH3, H is there. Cl, CH3 and H is there. This carbon atom, CH2, HCl is there. CH3, HCl is there. Okay, but that is not the way you have to look into that. You have to write the Fisher formula for the first one. I will just write for the first one. If you take up this, you can see that H is written like this and Cl is written like this, and you have got one CH3 here and another group which is CH3 CHCl. Okay, so if you look at this, this is with the last priority. The first priority will be 1. This is the second priority because of the bulky group. This will be the third priority. Okay, so you can see that 1, 2 and 3 go in the S direction, that is anti-clockwise direction. If you put up for this, this will also be having S direction, but if you put up for this will have our priority will be changing. Okay, so it is important that you can rotate around carbon-carbon single bonds to make sure they get a different conformation. So here it is conformation asked. So this will be S and this will be S, while this will be R. That is what it means. To rotate the molecule in 3 dimensions to compare the chirality. Model fits are useful. Another way to determine each of these chiralities is to determine the configuration of each of these chirality centers. In this case, the priority of the substituents is Cl, CHCl, CH3 and CH3. So this is what I think we have drawn. Okay, this priority is here we have put 1, 2 and 3. It is already given there, right? So for example, the configuration of the chiral centers of the compound are both yes. However, 1 and 3 are not identical. 1 and 3 are not identical. You can draw them, and therefore only 2 and 3 are identical. So we move on to question number 7 there. Next one. Which of the following is can exhibit geometrical isomerism? 1 hexene, 2 methyl, 2 pentene, 3 methyl pentene, 2 hexene. Okay. So hexene is, you can see you can have a double bond there. That means all the hexene compounds can exhibit geometrical isomerism. But what is the question? Which of the following compounds can exhibit geometrical isomerism? 1 hexene means, what is that? Is asking the hexene. Okay, we'll draw first the simplest structure like this. Right? So if we start numbering there, 1, 2, 3, 4, 5 and 6. Okay, so if we start numbering like that, so you will have its first compound is 1 hexene. So it is having a double bond there. Right? So if you have a double bond there, you can have 1, 2, 3, 4, 1 H here, another one, another H here. Right? So there will be some bulky groups downwards. So keep in mind, this will give geometrical isomerism or what? This will give geometrical isomerism, I think not, because of there are several isomers of hexene, and depending on the position and geometry of the double bond in the chain, one of the most commonly used isomer is 1 hexene. I think you got 1 hexene or 2 hexene, both are the right answer there. 2 methyl, 2 pentane and 3 methyl, 3 pentane. I know they don't give pentane. All of them give geometrical isomerism. So what about 2 methyl, 2 pentane, 2 methyl, 2 pentane? You can draw this structure. If you write the second structure there, it will be coming like you have to first put pentene. This one I am writing B. Okay. 2 methyl, I am numbering from the right side. If I number from right side, 1, 2, 3, 4 and 5. They come like this. And 2 methyl is there. 2 pentene is also there. So here you have got a double bonded compound also there. So here you will have H and here you will have H, H, H. H and H everywhere. So this is also going to give you a geometrical isomerism because you've got double bonded compounds there. So what is the question? I don't understand. Which of the following compounds can exhibit geometrical isomerism? Wherever you have double bond and this is also you have CH and H here, CH3 here. So you can get a geometrical isomerism for this only when they are connected with the second carbon atom. For the first carbon atom, you will not get this. So I think all of them are giving except A, all of them are giving the uh, geometrical isomerism. So the answer is, I think the question should be like this: which of the following cannot exhibit geometrical isomerism? One hexene this cannot exhibit only unless you have this two hexene. No, the answer is A. And explanation is some other thing. There are several isomers of hexene depending on the position, the geometry of the double bond of the chain. One of the most common industrial use for isomer is 1-hexene and alpha olefin. So it is 1-hexene only. The answer is not D, it is A. So first position itself, you don't usually get isomers. You have to define the second position because you will because means if you put a double bond here, it gives two similar compounds there, this one and this one. Therefore, you cannot have cis or trans isomerism. So if it comes to the second position, you can get one group here like this CS3 and another group like a polyky group there. These two are different groups, so you can have that. So the answer is actually A. Okay. Next question is how many number of stereomers are possible for 2,3 pentane diol? 2,3 pentane diol. Let us look into the first answer is how many isomers it is asking. 2, 3. I mean it's 3, 4, 5, and 6. Is it? 3, 4, C is 5, and D is 6. And answer is B. 2,3 pentane diol contains 2 chiral carbon atoms, so the number of possible stereoisomers is 4 is given as like that. So again, you can write it. Can you write that? What is that structure? 2,3 pentane diol. Pentane means you should first write the 5 carbon atoms. Okay, so then we write the numbering there: 1, 2, 3, 4, and 5. Okay, then we write 2, 3 is having diol. This is having one OH and this is also having one OH. 2, 3 pentane diol. Okay, then the rest of the things is you have to fill it up with hydrogen atoms there. H, and here you will have one H, and here you will have one H. Here you will have H and H and H, right? This goes like this. So in short, what you get is this will be a C2H5 group there, and this will be a CS3 there, and this will be OH here, and this will be H here. So you get a chiral center there for this one, and similarly you get a chiral center for this one. So the answer is B. You get the 4 isomers. Two chiral carbon atoms are there, 1 and 2. So 2 power n is equal to 4. And maybe if they ask if there is mirror image of the same, if you have CS3 here, then you will get a mirror image, mirror plane. If you get mirror plane, 2 isomers will be same. So 2 isomers will be same means 2 will be equal to 1. Therefore, you subtract this minus 1 from that. So you get 4 minus 1 equal to 3. In case both of them are CH3 same. Okay. Now let's move on to the next question. How many chiral stereoisomers can be drawn for CH3, CHF, CHF, CH3? Okay. So you just put up all these CH, C, 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 CH3 twice. There are about 6 carbon atoms there, and we can connect them like this. So you have CH3 here, the first one, CH3. Second one is CH and F there. Third one is CH and F, another one. Third one is another CH and F there. Fourth one is CH, CH3 twice it is given. That means, you have got one CH3 here and another CH3 here. So how many chiral centers are there? So this will be one chiral center and this will be another chiral center. Right? This is similar and this is also similar. So 2 power 2 equal to 4. So there will be 4 isomers. So the answer is, I think probably yes, there is 2 chiral atoms. So the number of possible isomers is A. The fourth one is the right isomer, right answer. Okay. So the next question is, I think connected with something is missing there. I can go to the bottom. What is the total number of isomers, stereoisomers included, designated by dichlorocyclopentane? Total number of isomers, stereoisomers included, designated by dichlorocyclopentane. So it is asking about a cyclopentane. It is asking about a cyclopentane. And you can start numbering from 1 dichlorocyclopentane. So any 2Cl I can put. Dichlorocyclopentane is there. And stereoisomers also it is asking. That means you have to put R and S. So for that I think you have to draw separately all the structures, all the 5 structures for that, in which cis molecule should be there and trans molecule should be there. So it is already, I think it is drawn there. The structure isomers, if you consider, you can consider chirality also. There are 2 chiral carbon atoms, because wherever you have got 2 chlorine atoms, the maximum number of stereoisomers is 2 for 2 equal to 4, which is the 1, 2 and 1, 2 dichloropentane should be there. And you can have 1, 3 also, but in the 1, 4 you can get 1 mirror. So the total estimation will be 7, I think. So let us see into the explanation. Answer is A. How? You got 2 possibilities there. This is H and this is H. Okay. Another one structure that I can write is, I can have a cyclopentane like this, and then I can have one Cl here, another Cl here. This will be 1, 2, and this will be 1, 2, and 3. So 1, 2 dichlorocyclopentane will be there. So this will be 1, 3 dichlorocyclopentane will be there. And 2 isomers, I mean 2 chiral centers are there. This is 1 chiral center and this is 1 chiral center. For this, if you see 2 power 2, you can get 4 isomers. Here also there are 2 chiral centers. Okay, but if you draw a structure like this, okay, in which you got Cl and Cl like this, same structure, you can see that you can draw a mirror plane. You can draw a mirror plane. Okay, here also you got 2 chiral centers there, so you should get 2 power n equal to 4. 4 plus 4, you should get 8 isomers. 8 isomers. But because you are having a plane of symmetry here, 2 isomers will be equal to 1. So you have to subtract minus 1 from there. So 8 minus 1 will be equal to 7. So 7 is the right answer there. I think that mirror image is given in the last slide. Is it that? Yes, here it is. Here it is. Okay. So you can get a mirror plane there. Because of that, you get 2 isomers. These 2 isomers appear identical. But if you have trans isomers, then the mirror images are not the same. So for 1, 2 dichlorocyclopentane, you got 2 isomers, which are mirror images. Therefore, 2 equal to 1. Here, this is 1 isomer and this is 1 isomer. So I can put it 1 plus 1 equal to 2. So this is 1 and this is 2. So you get 3. 3 isomers for 1, 2 dichloropentane. 4 isomers for 1, 3 dichloropentane. So 4 plus 3 equal to 7. That is what is the answer there. So I think you have understood. You can just work out, and if you have any doubt, you can ask me in the Google Classroom. Thank you for joining me.